Okay. So, as I said, what I want to do for the second half here, and I'm not sure if it'll take us the whole time, but we'll just see how it goes. What I'd like to do is talk you through the 4 different modal systems that we're going to have. And the way to kind of do it is by thinking about various modal logic semantic concepts. These are going to parallel ones that we've defined for TFL and for FOL, but they're going to have particular, we'll call it, modal flavoring to them. So let's go ahead and get started with our first 4. And these are really going to be the ones that we're interested in. So I'm going to just throw them all at you and we'll talk about them one by one afterwards. So first we can say that an argument is modally valid if and only if there's no world in any interpretation, right, in which all of the premises are true and the conclusion false. So note what this is doing is it's basically saying that, hey, there's no possibility at all, even within any model, where the premises are true and the conclusion's false. And it's worth noting that this arguably is capturing the notion of validity, at least as we initially presented it, better than any definition we've seen so far. Because there's going to turn out to be lots of arguments that will be, say, valid in TFL that are not going to be modally valid, because we can play around with accessibility and start to include modal operators. So modal validity. There's no world in any interpretation where premises are true and conclusions false. We can then say an individual ML sentence is a modal logical truth, if and only if it's true at every world in every interpretation. So again, not only now is it going to be true in every valuation, but it's true in every valuation in every interpretation that we could possibly construct. On the flip side, we can talk about modal contradictions. Right? We can say that an individual sentence is a modal contradiction if and only if it's false in every world, in every interpretation that we can construct. So nothing really shocking in all of those concepts, right? And finally, the really easy one, if you like, easy to satisfy, we can say that an ML sentence or some sentences are modally consistent if and only if it's true, or they're all true together, at some world in some interpretation. Right? So all this really means is that there's at least one model and one world and at least one model where this sentence is true. So notably, right, these are, as I said, parallel to the concepts and definitions we had before, but they're just kind of tweaked. So modal validity, right, there's no world in any interpretation. Modal logical truth, it's true at every world in every interpretation. Modal contradiction is false in every world in every interpretation. And consistent, modal consistent, it's true at some world in some interpretation. There's some model we can build. Now, the thing to note is that every one of these is also going to have to be relativized. And what I mean by that is, there will be certain arguments that will be modally valid in one of our modological systems, but will not be modally valid in other ones. And this is because certain accessibility relations will give us different possible models. So again, more on that in a second. But the key thing is that we can have these in the back of our minds. The big thing is that using modal interpretations, we can introduce yet another reading of the double turnstile. So if you remember, so far we've used the double turnstile in TFL to express tautological entailment. And we've used it in FOL to express logical entailment. Well, here we're going to use it to express modal logical entailment. But in fact, I'm not just going to give you one, I'm going to give you four. Right? So we'll have, whenever we're dealing with modal logic, as well as the double turnstile, there'll have to be a subscript on it. And the subscript is telling us which of our modal systems we're using. So I'll briefly introduce you to the names and we'll talk about them. So we have K, T, S4, and S5. Very, very easy and obvious names. Right? But the difference between these logical systems is the restrictions they put on accessibility. K, which is named for Saul Kripke, who came up with this semantics. Right? K has no restrictions on accessibility. You can draw whatever arrows you want. This means that actually just a world existing in a vacuum with no accessibility relations whatsoever is a valid model in K. In fact, all of the models we've looked at, all of the interpretations we've looked at, only work as interpretations for K. So it has no restrictions. Draw whatever arrows you want. It is an extremely weak modal logic. The next logic, T, requires accessibility to be reflexive. So that is, every world can access itself. And this is actually going to be really useful because there's one kind of intuitive entailment that fails for K. More on it in just a second. But again, so T requires accessibility as reflexive. Every world's got a loop. S4 builds on that. S4 says, okay, accessibility is reflexive, but it also has to be transitive. Right? So if world 1 can see world 2, and world 2 can see world 3, then there has to be a direct accessibility relation from 1 to 3. Right? If there's a chain, then the one at the base of the chain can see the top of the chain. S4 is a very good modal logic for thinking about time. Because, right, think about the earlier than relation, right? If this moment is earlier than that one, and that one is earlier than a third one, then your first one damn well better be earlier than the third one. Okay, so again, S4 is reflexive and transitive. S5 is the equivalence relation. S5 says accessibility is reflexive, symmetric, and transitive. An upshot of this, according to S5, is that effectively every world can see every world. This has some very interesting consequences when we start to iterate modal operators. Now, which one of these systems is best? It honestly depends on what you're trying to do. If you're trying to capture something like temporal logic, S4 is probably pretty good. You especially don't want symmetry. If you're trying to capture, I don't know, logical possibility, something like S5 is probably where we want to go. Maybe. Again, there's reasons to use these different systems. One of the very interesting things is we can also use modal logic to map deontology. That is, we can understand the box as must and understand the diamond as should. And then if you do that, you're going to want a very, very, very weak logic. You're probably going to want something like T or maybe even K. Because as we all know, right, should does not entail is. Just think about all of the times you didn't do what you should have done. But again, what's important for our purposes is these 4 different systems can all be used to characterize this double turnstile. And it's going to behave the same as it did before. The sentences on the left will double turnstile the sentence on the right, if and only if. Right? There's no world in the interpretation that makes the sentences over here true and the sentence over here false. So let's talk through these one by one. So here's an interpretation, right? We've got 3 worlds. We've got world 1, world 2, world 3. Our arrows again indicate accessibility. Note that this interpretation is suitable for K, but it's not suitable for any of our other restrictions, right? None of our other systems. So we can ask, if we want to make it suitable for system T, what do we need to add to the graph? What accessibility relations, exactly, right? The accessibility relations we need to add, every world needs to see itself. So we need to add loops for world 2 and world 3. Everybody see that before we go anywhere else. So here's an interesting question. In this interpretation, as it stands, is box A true or false in world 3? Let's think. Is every world that 3 can access an A world? Okay, cool. So box A is false. How about box negation A? Ooh, interesting. How many worlds does 3 access? None. Yeah, it don't see nobody. So some weird things. Is diamond A true in 3? Is diamond not A true in 3? 3 looks pretty gross, right? 3 doesn't really have much of nothing going on, right? Again, things just to kind of think about here, right? What happens with these relations turn out in this kind of funny way? Here's another one. Is box A or not A true or false in world 3? Again, I'll give you. Box A or not A. Is that true or false in world 3? It's false. It's false. Right? How fucking weird is that? Notably, right? Is A or not A true or false in 3? So again, let's take this. Is this sentence true or false in world 3? Right? This sentence is true. Right? Why is it true? Because in order to figure out the truth value for the disjunction, you just look at the world. You don't have to care about accessibility relations. They only come in when we start to think about boxes and diamonds. So here we just go and look. Is at least one of these 2 true in world 3? Yes, A is true in world 3. So A or not A is true at 3. But we stick this in front. If we put the box in front, is the boxed sentence true or false in 3 in this interpretation? Now it's false. Because not even one world that it sees is such that this is true. So you get something very weird, right? Something can be true, but not necessarily true in this very strange way. Yeah. Yeah, that's the other fun thing, right? If we replace the box with a diamond, still false, right? Something can be true and not be possible at a world in K. That's fucking weird, right? Okay, so we can start to increase the restrictions here. If we add in the loops, we get a model that's now acceptable for logical system T, right? This is where every world sees itself. Note, here's an interesting thing. Think about this claim now. Diamond, this disjunction. Is this going to be true or false at world 3 now? Right? Now that we've added the extra accessibility relations, this is now true at 3. Importantly, once you add reflexivity, you will never have a world that sees nothing. It will always have to at least see itself. Okay, so now we've got an interpretation compatible with logic T. Note, it's still compatible with K, because K has no restrictions, but that also means you can make as restricted a one as you want, and it's still going to suit K. So what would we need to add if we're going to get S4? Taking our interpretation, this isn't suitable for S4. What do we need to add to make it suitable? So S4, accessibility needs to be reflexive and transitive. So what's missing here?
World 1 would need that narrow to world 3.
Exactly, right? Because 1 can see 2 and 2 can see 3. So if the relation is going to be transitive, 1 needs to be able to see 3. Because here's something interesting. Is diamond not B true in world 1? Diamond negation B. Is that true in world 1? I mean, as it stands, is it? No, right? Because it can't see 3. So we add that. And now diamond negation B is going to be true at world 1. Right? And finally, we have to make it an S5 relation where it needs to be reflexive, symmetric, and transitive. So what's missing? Every arrow needs to be double-headed. Every arrow needs to be double-headed, right? So the one that goes from 1 to 3, we're now going to have to give it from 3 back to 1. And similarly, the relation that goes from 2 to 3, we need to go backwards. Cool. So again, what you get here is there's a direct connection from every world to every other world. Again, just sort of stuff we talked about last week, just now applied to our frames. Now, why would we bother with these kinds of things? We start to get different results with the different systems. Because the changes in accessibility will deliver different modal results. So let's talk about system K for a second. Here are some things that are true in K, and hence will also be true in every other system. Right? First, if you have a box attached to a sentence, and you have a boxed conditional, somebody's excited, a boxed conditional of the form A conditional B, you then can derive box B. If box A and box A then B, you know that box B. Put another way, if A is necessarily true, and if A then B, you know that B has to be necessarily true as well. The other ones have to do with the interplay between boxes and diamonds. We can define boxes and diamonds together. So we can say that, right, to take this first one, if it's not necessarily not the case, then it's possibly the case, right? So negation, box, negation flips to diamond. Put another way, if not everyone isn't, then someone has to be. We've actually even done this when we were thinking about the relationship between quantifiers. Negation, universal negation could be changed just to the existential by itself. Similarly, if it's not necessarily true that A, then it must be possibly A. There'll be one breakdown here, but we can play with that. We also get, right, if necessarily A is false, this is our third one here, if necessarily A is false, then it's not the case that A is possibly true. These are just different interdefinitions of these operators. We're not really going to play with them, but it's useful to know. But here's the biggest weirdness that we can get with system K. We've seen it in a way. Something can be necessarily true, but that doesn't entail that it is in fact true. Take this model. Is box A true in world 1? So is box A going to be true at world 1? Well, every world that one can see is an A world. So box A is true at world 1. But note, is A true at world 1? No. So that's very strange, right? A's being necessarily true on K does not entail that it is in fact true. That's fucking weird. Right? Because again, why? In order for the box claim to be true at world 1, every world it can see must be one where A is true. It can only see 2, and 2 is a world where A is true. So box A is true at 1, but A is not true at 1. This is actually one reason to have this system. It's a very good system for thinking about moral obligations. Right? The fact that something can be obligatory does not mean that it is in fact obeyed. So that's one reason to have a system this weak. But here's the cool thing. If we move from K to T, this issue is blocked. Because if we make sure that every world can see itself, then we will prevent the kind of case where that gives us box A. We add the accessibility relation, we get, or if we have the reflexive accessibility relation, we guarantee now that box A entails A. Because you have to see yourself. So you then will be one of the worlds where A is true. So the thought here is that by moving to T, you buy into a pretty plausible idea, which is that necessity implies actuality. Something being necessarily true implies that it is true at the given world. But we still have some oddness with T. Here's something strange. Right? Take world 2. Well, let's give you a better example. Take the line that's red in the bottom there and consider this interpretation. It's a slight variation on the one we just did. So here we've got worlds 1, 2, and 3. It satisfies the condition of reflexivity, right? But we also have 1 can see 2 and 2 can see 3. Now here's something very strange. A's being necessarily true doesn't entail that necessarily A is necessarily true. So here's the thought, right? What might be necessarily true for me isn't going to be necessarily true for you. Why? Because there might be possibilities available to you that aren't accessible to me. So here we go. Just take box A. Right? Is box A true at world 1? Is it true that every world 1 can see is an A world? Okay, yeah, right? It can see itself, which is an A world. and it can see 2, which is an A world. Cool. Is box A true at world 1? So how do we assess that, right? We can assess it this way. Is every world that one can see a world where box A is true? Right? Is every world that one can see a world such that every world it can see is an A world? 2 can see 3, right? So here's something strange, right? Something can be necessary, but only contingently necessary. What is fixed, what must be true, that can change. Right? That's weird. That's fucking weird. Right? But again, it sounds plausible if we're thinking about potential, right? I do not have the potential to do certain things in my 30s because that's in the past for me. You guys do. So if we think about these kind of mapping potentials, there should be certain accessibility relations that will be blocked. Or me. That will be open relative to you. Again, we can hopefully get cases of this sort of thing. But we can then block this weirdness by moving to the next system. If we move to S4, we block this case. So what does S4 require again? It needs reflexivity, but what's the other feature that it requires of accessibility? Yeah, it's got to be transitive, right? So if we're going to make this model transitive, what do we need to add? One's got to go to 3, right? One's got to access 3. And as soon as we do that, right, the entailment problem is blocked. Because 1, it's no longer the case that box A. So here's something cool. Once you get to S4, you can add boxes as much as you want. Because if you have like 40 boxes and then a sentence, that is the same as just having 1 at the beginning. But what's strange is that if you have different operators here, if you have, say, a box and a diamond, then you can still get a failure of entailment. So for example, let's take our little system here. Can we find the counter model here? Yeah. Yeah, world 3, right? So look and see, right? Is it such that we have a world where diamond A is true? Let's just see. Can we find a world where diamond A is true? Yeah, I mean, we can think of a couple, right? A is true here. So diamond A is true here. Diamond A is true here. Diamond negation A is true here. Right? But is box diamond A going to be true? Why does it fail? So where does it fail? Where? Yeah, nice. If we look at world 2, we have first part true, second part false. Hey, lovely. Because it is a world where A is possible, but it can access a world where A is not possible. So the fact that A is possible doesn't mean that it's necessarily possible. Not every world it can see is a world that can see an A world. And I know that sounds confusing, but again, just think about it in terms of the process, right? To make the box true at a world, everything it accesses needs to make what it's boxing true. And then inside that could be, say, a box or a diamond. So how do we then get this to come out right? Easy peasy. We move to our last model, our last system, where we add symmetry. So what would we need to do to change this to make it satisfy S5? Yeah, right? Every arrow becomes double-headed, right? So now every world in our collection can see every world, and this means that whatever's possible for one world will be possible for every world. So the very interesting property with S5 is that if you have a string of modal operators, say you have just a weird string, in S5, that's equivalent to just the diamond. You can eliminate or ignore all of these iterated modal operators down to the base one, because if it is true, all of the rest will be true as well, which is very cool. But again, this will fit for certain systems, not for every aim that we want to do. Okay, good so far? Questions on these general ideas? Again, K, no restrictions. T, reflexivity. S4, reflexive and transitive. S5, reflexive, symmetric, transitive. One of the things we'll be able to do, and this is in fact what I'm going to ask you to do, is I'm going to ask you to use ML interpretations, to make them, to construct what we'll call counterexamples, countermodels, counterinterpretations. These are ML interpretations designed to show that certain entailment claims are false or that they fail on given modal systems. So, for example, think about this one. How we might generate a counterinterpretation for that entailment. So what does a counterinterpretation need to do? Right? It needs to make the thing on the left-hand side of the entailment relation true and the right-hand side false. Again, this is what we're going to talk about in the tutorials this week. But the general thought here is going to be doing the sort of stuff we've been doing. You give me the boxes with certain atomic sentences being true or false, draw the accessibility relations in such a way that they make the premises true, but leave the conclusion false. Note that every one of these has a subscript. So that means depending on what subscript the thing is, the accessibility relation is going to have certain features. Right? So if this was an S5, say, you've got to make sure that, right, reflexive, double-headed arrows, and the transitivity. Right? But of course, K, draw whatever arrows you want. Again, we'll start off with some in K, but most of the interesting ones might feature some of these others. We'll talk more about how to do these in the tutorials, but the basic idea is hopefully pretty clear. Okay. Before we go any further, questions so far? Feeling okay? Okay, cool. So here's what you should now be able to do, or at least start to, right? If I give you an ML interpretation, you should be able to read from that whether certain or what ML sentences are true or false at given worlds. And similarly, at least to start, of constructing ML counterinterpretations to show me that in a given system, certain entailment claims fail. Note, I'm always going to ask you to give me a counterinterpretation. That is to show me that an entailment fails. Because interestingly, this system will not allow you to show that an entailment holds. In order to do that, you would need to think about every possible model that you could generate. And that's going to use up a hell of a lot of paper. That's just not something that can be done using this kind of system. We can produce counterexamples. We cannot support claims. So the important things to remember here with this system, right? Every sentence that we will see is going to be true or false at a world. Every claim is going to be relativized. ML sentences that don't feature modal operators are just like basically what we would do with valuations. Right? Certain atoms will be true or false, so then you can just read off what the connectives are, what truth value the connectives have. It's only once you get the boxes and diamonds you need to worry about accessibility. And the thing to remember with these is that the box is true if every accessible world, the diamond is true if at least one accessible world. And finally, our four systems are all characterized by having different restrictions on accessibility. There are no restrictions in K. T is reflexive. S4 is reflexive and transitive. S5 is all three: reflexive, symmetric, and transitive. Okay, cool, nice. So as I said, what we'll do in the tutorial is we'll go through a couple of these. I'll give you some sample interpretations. We'll play around with what's true or false in them, and we'll start on generating our own particular counter interpretations. You can kind of expect that I'm going to ask you one of each type of question on the final exam. Hence why I'm trying to make it really clear what you need to be able to do. Okay, so what are we going to do next week? Next week is the start of the real fun, because next week we are going to start in on our proof system. And the aim of the proof system, as I've said a couple times, is to get us to be able to fill in the gaps for FOL. There was so much stuff in FOL we couldn't do. We couldn't show that a sentence was a logical truth or that an argument was valid. This is where natural deduction comes in. So please, for next week, read the chapter here from For All X. If you don't read it, it's just going to be really weird. So have a read over it. We'll then talk about how the rules work next time. But more importantly, take care of yourselves. Have a lovely rest of the day. And we'll see you all in the tutorials later this week.